Newtonian physics describes this motion as an invisible force. Earth's mass pulls the phone, dragging it downward until it impacts the ground. Einstein proposed a different perspective. He suggested that once the phone leaves your hand, it enters its most natural state, freefall. In this state, the phone is perfectly stationary and weightless within the fabric of space and time. The motion we observe comes from the Earth itself. Pushed by internal pressure, the ground accelerates upward, intercepting the phone in mid-air. Accepting this requires setting aside human intuition. Our senses tell us the floor is still and the phone is falling, but relativity suggests our perspective is reversed. In 1907, Einstein realized that a person falling from a roof would have no sensation of their own weight. This happiest thought suggested that freefall is not a state of being pulled, but a state of being free from all forces. And this is the daily reality for astronauts on the International Space Station. Though they are 400 kilometers high, they remain well within the Earth's gravitational reach. They float because they are in a state of perpetual freefall, dropping around the curve of the planet. Because the station and everything inside it fall at the exact same rate, the sensation of weight vanishes. Weightlessness is the baseline state of the universe. The heavy sensation you feel while standing on the ground is the physical evidence of the Earth's surface resisting your natural state of fall. Standing inside a windowless elevator, you feel your feet pressed against the floor. This sensation is produced in two identical ways: resting on Earth's surface or accelerating upward through deep space at 9.8 meters per second squared. No experiment performed inside the box can distinguish between these two environments. Dropped objects hit the floor with the exact same speed, and scales record identical weight in both scenarios. The equivalence principle states these scenarios are physically identical. Gravity is the same phenomenon as acceleration. If gravity is actually acceleration, we must explain what guides the moon in its orbit, or an apple to the grass, without using the concept of an invisible pole. Einstein's solution was spacetime, a four-dimensional fabric that mass physically warps. A planet creates a literal curve in the universe's geometry. Objects follow the straightest possible path, a geodesic, across this warped environment. A straight line on a curved surface naturally becomes a circular orbit. Planetary motion is not a balance of competing forces. It is simply matter moving in a straight line through a curved environment. Visualizing this as a weighted fabric only captures part of the reality. The most significant warping happens not in space, but in time. Mass slows the passage of time. A clock at sea level ticks slightly slower than a clock on a mountain peak because it is closer to the Earth's mass. Because an object occupies a physical height, time passes at a different rate at its base than at its top. This temporal imbalance creates a gradient, a direction in which the universe naturally flows. Physical matter naturally drifts toward the region where time moves the slowest. This is the mechanism that keeps us pinned to the Earth. Newton's laws remain a highly accurate approximation for most human activities. At low speeds and moderate distances, the discrepancy between his math and Einstein's is nearly impossible to measure. Modern space agencies still utilize Newtonian mechanics to calculate the trajectories of most satellites and interplanetary probes. Newton provided a way to calculate the effects of gravity. Einstein provided the explanation for why those effects occur. However, when we encounter the intense gravity of stars or require the extreme precision of GPS networks, Newtonian math fails in these environments. The geometric reality of general relativity is the only way to achieve accuracy. Proof of this geometry arrived in 1919 when Arthur Eddington observed a total solar eclipse to see if the sun could deflect starlight. The photographs showed that the sun's mass physically bent the path of light from distant stars, exactly as Einstein's theory predicted. Further confirmation came with the detection of gravitational waves, actual ripples in the fabric of space-time caused by distant massive collisions. We have now seen the theory pushed to its limit, black holes, where the curvature is so severe that even light is trapped. Mass dictates the curvature of space-time, and that curvature dictates the path of matter. In the next episode, we will explore the consequences of this relationship, the formation of black holes, the potential for wormholes, and time travel.